you can count the number of elements to the n, then there is a finite group. If you cannot, like the set of integers, you know very well that the set of integers, you cannot exhaust all integers, then you see there is an infinite group. And you see I was talking about this. And what I wanted us to do is to talk about this with respect to showing whether it is a group or not. And here, let's see this. I think, I think that is where you lost me. And please don't hesitate, you guys, and especially the representative, in case you lose me, and at times this one happens technologically, I'm very much alert with respect to my WhatsApp. So just in case you lose me, just drop a WhatsApp immediately. Is that okay, Ben? I think that is it, so that at least we be together without using each other. But I think someone has unmuted again. Kindly please mute. So you see, look at this. You will see we told that, okay, we have this to be a group, the set of integers equipped with the binary operation addition, and we told that there is a group. Let's see how that is a group. Yeah, I can see there is an issue with my device. My device is misbehaving, but anyway, no worry. I think we shall overcome. Okay. Let's see. Okay, so here we have this. You see, that is the set of integers equipped with the addition, and this one is what you call, in fact, it's an additive abelian group. And what do we mean by abelian? Look at this. You see, it's important that we see abelian. If you see, it does not matter the order in which you arrange them when you're adding. And I think that is what applies to integers. But before we get there, let's see whether the first one is true. You notice that at all times, let's see this, let A, B, C, all these be integers. I think there is something that you know at all times. Whenever you add any two integers, you'll always have another integer. You see, now this one is G1. You see, for every two integers that you add, you'll always have another integer. And just in case for those fellows who've forgotten what integers are, I'm talking about, you see all number values, both negative and positive, including 0. And of course, if we use, let's say, the number line, maybe that is why I'm using a different ink here. Of course, those are integers 1, 2, 3, and that continues that way to the left, -1, -2. All those that are represented by these points are integers. To the left, they are negative. To the right, they are positive. And you know very well that whenever you add any two integers, you're going to have always another integer. And that is it. When we look at the second property, D2, you see that it does not matter how you add. You see, like this is no different from A plus B plus C. You could pick even any two integers. That is for every A, B, C, in, of course, for every three integers. And that is exactly the case. You could pick any two integers. Like here, when you look at G1, -3 plus -2 is -5. And -5 is also another integer. 1 plus 2 is 3, so that is also another integer. 0 plus -1 is -1, that is another integer, and so on. Now, when we talk about property 2 here, -3, let's say, plus -2, let's say, plus 1. You see, when you say -3 plus -2 is -5, plus 1 is -4. And what we've seen in that case is that we've started with the first two and then followed by that. But it is no different from isolating it and then having -3 plus 1, that is -1. So you see, you deal with those ones first, that is -2 and 1. What we have is -1 plus -3 is -4. And you notice that the left-hand side is the same as the right-hand side. So that is what we call associativity property satisfied. Now in D3, and I wish to have each one of us to see this clearly. In G3, what do we see? We are trying to see whether the set of integers has what we call the additive identity, or rather the identity element. And what do we see here? Look at G3. In G3, there exists an element, there exists, what is the additive identity here? It is that element that when you add, because we're dealing with addition here, when you add to any other element, right? Is something that you should have in mind. When you add to any other integer, you will always have that other integer without changing. And that element is 0. You see, this one is the additive, we call it here the additive identity. You see, because we're talking about the operation, binary operation is addition here. So the additive identity, you see, and this identity element, like that, you look at this, like that, and it is the case here that 0 plus a is no different from a plus 0, and all these will give us a for every integer. That is, you see, for every a in the set of integers, meaning here that you see a represents any integer, and it is true that whenever you add any integer to 0, you'll always have that other integer. Now, let's go to G3, G4, sorry, the fourth property. And you will agree with me that for every integer, let's say a in Z, there exists an element minus a, you see? And this minus a, what do we see here? Minus a at all times, you see negative a plus a. This one is no different from a plus negative a. This one will always give us the identity element 0. You see? And look at this. The additive inverse of, let's say, negative 2 is 2. Because negative 2 plus 2 is 0. The additive inverse of negative 1 is 1. It is negative minus into negative 1. You see, that is exactly what we're talking about here. The additive inverse, if we have negative 1, then you notice that, yes, if we have this to be negative 1, to be an integer, then its inverse is minus into negative 1, which is 1. So the additive inverse of, let's say, 3 is negative 3. The additive inverse of negative 2 is 2, because when you add negative 2 to 2, you will have 0, which is the additive identity. So the test for the additive inverse is that that element that you call the additive inverse of the other element should be that when you add the 2, it should give you a 0, the additive identity, in as far as the set of integers is concerned. Now, the reason why I said it is abelian is because, look at this. Let me use this other page, and kindly please allow me to enlarge. You see, look at this. Why abelian? Because it satisfies what we call commutativity property. And here, the commutativity property, look at this. You notice that a plus b is, it doesn't matter how we add integers. You'll always have the same integer for every a, b in the set, for every 2 integers. And you can easily tell that. Like, for example, if I may use different 2, this one is too faint. 2 plus 3 is no different from 3 plus 2. 4 plus 8 is no different from 8 plus 4, and so on. So what we see in that case is that then we see that that is why we're saying that the set of integers equipped with addition is, look at this, I said here, is an additive abelian group, because it satisfies these 5 properties. The 5 properties for a group, and then followed by, of course, this one, commutativity, followed by commutativity. Right? That is it. So that is why we have that. Now, let's go back. Let's go to this. We are done with this now. You see, the set of integers. We've called it I here, but I discourage using I. it has been called a year, but let's use the set of integers the usual way that we have. And you notice that we are simply dealing with the same year. And you can see we've gotten to the point where we're saying that it is an abelian group. But now, because it is an additive abelian group, then it is a module. Now, let's look at this. The set of integers, kind of look at this. But now, that not really integers, the set of all non-zero rational numbers. This is also important to note, and you'll also allow me to use this. Let me use this page. That we told that let's go back to that. What is our conclusion here? We told that it is, in fact, it is also an abelian group. Yes, because it satisfies commutativity under multiplication. This one is multiplication. So let's see whether that is the case. You see, for us, even before, what do you mean by, you must have a clear understanding of what we mean by the set of rational numbers. You see, that is the set of rational numbers. There's any rational number, a set of rational numbers are in this form, A over B, where A and B are integers, and B is not equal to 0. You see, that is how rational, that is how they look like. You see? Yes. Examples of rational numbers so that you can have an understanding, like I have 5 over 2. Even whole numbers, because 3 is the same as 3 over 1. Negative 5, all this is the same as negative 5 over 1. Yeah. You see? Negative 5 alone, as it starts there, is the same as 7 over 1. You see, that is the disadvantage, as I said. You lectures, I'll remove monkey just in case you are not, just can you please mute yourself? Yeah. If you do not attend a virtual engagement in a conducive environment, then it is simply an attempt in futility. So it is important that you always have a conducive environment to concentrate. Just like if we had asked for a physical class, then you could have otherwise been in a specific area, a lecture where you go concentrating. So here we're talking about, you see, these are rationals. Now, even if we draw, if we draw, and although the number line does not represent the set of rationals, all rationals, you see, all rationals except 0. So we're saying that here we're talking about non-zero rational numbers. All numbers that can be expressed in the form A over B, where A and B, the numerator and the denominator are integers, and the denominator is not equal to 0. Those ones are what we call rationals, non-zero rationals. What we are told is, of course, there is a Q naught there to represent that. So we're told that Q naught, look at this, together with multiplication, this one is an abelian group. You could be asked to show that the set of non-zero rationals is an abelian group. What we need to do first is it true that whenever, of course, we let's say A, B, C, all these to be members of non-zero rationals, or to be non-zero rationals, we know very well that whenever you multiply any two rationals, it will always give us a rational. You see, for every A, B in the set of non-zero rationals. In the second one, you see rationals like maybe I should have picked some few here. The ones I've talked about. Half multiplied by 5 over 2 is 5 over 4. That is also a rational number. Half multiplied by 3 over 1 is 3 over 2. That is also a rational number. It's in the form 3 over 2, the form A over B, where A and B are integers. Half multiplied by negative 5 is negative 5 over 2. That is also in this form, where both are. All this, you always have another rational, and that is why we're saying that it satisfies such associativity property. Again, if you have A multiplied by B and then multiplied by C, this one is no different from A multiplied by B, C multiplied by C, where the last two start. You see? This is what we call associativity. And you notice, look at even this, the ones that we picked here. If we pick this, if we pick, let's say this, let's talk about this one. Let's talk about this one, and this one, and this one. These are three non-zero rationals. I have multiplied by 5/2 is 5/4, multiplied by this is negative 25/4. This is no different from picking this first multiplied by this. We shall have this to be negative 25/2 multiplied by a quarter. It will also be negative 25/4. So it does not matter whether you start with this was followed by this, or you start with this one and this followed by this. That is what we call associativity. Now, the third one, we would wish to see whether this, what is the identity here? See? And you notice that there exists one in the set of, look at this, and it is true. One is also a rational number. One is also a rational number. A rational number. What's happening here? I'm losing this guy. I want to admit him, but I'm not saying it. He's disappeared. Probably it's not. Now, one, look at this carefully here. One is also a rational number because it is in the B. One is the same as 1/1. What is this one called tip? You see, because you see that the binary option. So we call it the multiplication. Like that. Look at this. 1 multiplied by A is the same as A multiplied by 1, which is the same as A. So you can see the identity element does not change any other element. Whenever you engage that operation for every A in the set of positive rationals. And therefore, 1 in that case is the multiplicative identity. Don't forget, when we're talking about 0 was the additive identity in as far as the set of integers is concerned. Now we see that, look at this, we're talking about the set of non-zero rationals equipped to, and we see that the element that has not changed the other one whenever you engage that operation, another element, is 1. Now, the third one, the fourth now, is the existence of, let's see, G4 for every A in, look at this, in the set of non-zero rationals, and I think you remember this, the symbol for the exists. Oh yes, I think I mentioned this last time. An element, look at this, and this is what we call multiplicative inverse. Look at this, an element. Kindly check this. This is A raised to the power -1, which is the same as 1/A, such that, look at this, like that. And remember, this one is also in, no, not in the set, come on. Not, we're talking about this one, not in the set of integers, but that is in the set of non-zero rationals. This one in the set of, look at this, that inverse also must be there, like that, look at this, like that A multiplied by A inverse, which is the same as A inverse multiplied by A. What do we see in this case? This one is the same as 1 by A by A. This one is 1. And this one is the multiplicative identity. The inverse, together with the inverse of an element, together with the element, of course, engaging that operation must give us the identity element. Again, we see that when we multiply any two, look at this, any two non-zero rationals, it does not matter whether you start with this followed by this or this one followed by this, you still get the same. Half multiplied by 5/2 is no different from 5/2 multiplied by half. The same case to this and this. 3 multiplied by -5 is no different from -5 multiplied by 3. The 2 will give us -15. So therefore, we see that it satisfies the set of non-zero rationals, also satisfy what we call the commutativity property. And that is the one that equips this group with what we call, or rather that is the one that makes it what we call an abelian group. You see, but remember, this is not a module. This is not a module. You must be very careful. This is not a module. Not that A plus, no, not plus, A multiplied by B is no different from B multiplied by A for every two non-zero rationals. Implying, therefore, that this is not only a group, but also an abelian group, because it satisfies this property. Now, maybe even I should do this. Look at this, is the set of integers equipped with multiplication a group? You see, earlier on, we saw that the set of integers equipped with addition is a group, but is this a group? Whenever you multiply any two integers, let's test G1. Whenever you multiply any two integers, you will notice always that you will always have another integer. So it satisfies property 1 for every two integers. When you multiply them, you will always have another integer. So it satisfies what we call the closure property. Let's go to G2. In G2, we see that A multiplied by B multiplied by C, let's say starting with the first two, is no different from A multiplied by C multiplied by C. This is the case. And therefore, the set of integers satisfy the second property. What do we call such a group that satisfies the first two properties? This one is a semi-group. In fact, that is what we mentioned last time. Let's see whether G3 is satisfied. Now, G3 is satisfied. Why? Because the set of integers has 1. And 1, when we multiply by any other integer, you will have that other integer. There exists an element 1 in the set of integers called this one. Indeed, this one is called a multiplicative identity. Multiplicative identity, or simply the identity, such that you can see, such that, and this is the case at all times, such that A multiplied by 1, which is the same as 1 multiplied by A, is equal to A for every integer, and it is true. When you multiply every integer by 1, you will always have that other integer. Now, what do you call that group, that, or rather that set that satisfies these three elements? What do you call it? That satisfies at least 3. It is called a monoid. In fact, this one up to here, we see that this is a monoid. In fact, you could be asked to show that this is a monoid. Monoid, yes. Now, let's see the fourth property. In the fourth property here, G4, we wish to see whether there is a multiplication. For the multiplicative to exist, this is something that you should have in mind. right? For the multiplicative inverse to exist, there is something that should be there. Yes, that look at this G4. For every integer, and this is interesting. Should we say let's not even say for every integer, because it's not the case. It's not the case. And let me give one case that does not satisfy this G4. 2, let's say, of course, or rather, let me ask one of you to give us any integer in his or her mind. Kindly, please give me an integer. One of you to unmute and just give one integer. 2. 2, perfect. That is okay. Thank you. Thank you, man. That is okay. So now look at this. 2, the inverse, the multiplicative inverse of 2 is an element that when you multiply by 2, it must give you the multiplicative identity, which is 1. Which element is that? Are we saying that it is a half? But now, a half is not a member of, it is not an integer. Are you saying that? Of course, you see 2 is an integer. The multiplicative inverse of 2, which is in the set of integer, which is an integer, is a half. But now, a half is not an integer. And yet the condition is that the multiplicative inverse must be also a member of that set. What does this mean, therefore? This means, hence, we see what that means is that hence G4 is not satisfied, implying that the set of integers equipped with multiplication is not a group. I think you can see some good stuff now. Let me hope that now you are better positioned in terms of showing whether a certain non-empty set is a group or not. Well, these are properties that concern groups. Yeah. One that I may think of taking you through is this. Yeah, because this one's these cells or even the cancellation. Yeah, this one also. Yes, but this one that has left, I asked you to ignore that. The case of left or right, yeah, that is not necessary. So in this case, where you could be asked to show for any 3 elements, you see A, of course, having that is for a group. We see that this one is the binary operation. This is the general binary operation, could be representing plus, could be representing multiplication. And we told that yes, if this is the case, then B is equal to C, what we call the left cancellation. This one is the right cancellation. You realize that this one's cancel, and we shall have A is equal to B. And this one is not anything challenging, because you see, since this one is a group, you notice that each one of these has a multiplicative inverse, because the fourth property must be satisfied. And that being the case, therefore, what you do is you multiply that so that this one is cancelled, A is cancelled, so that we remain with this, and multiply both sides by the multiplicative inverse of A. When you do that, that is exactly what we've done here. And because of associativity, this one is the same as this because of associativity. And you can see by property 2, which is associativity. So this one multiplied by this, of course, is the identity. Why? Because of there is property 4. And property 4 tells us that if you have the inverse, then you multiply the inverse by the original element, then is equal to E. And now that is E, and you can see A inverse by A is E. But now we know that by property 3, the identity element does not change any other element. And that is why this multiplied by this will be B, and this multiplied by this will be C as required. And that is exactly what is required in as far as that is concerned. So what we're supposed to do next, what we shall do in this case is just by mentioning, but I think we can talk about this. Well, I don't intend to take you through those properties of groups, so you need not worry about that. What we're supposed to have here, there is something that I wish to take you through here in the few minutes that are remaining. And this entails what we call the additive group modular, not necessarily only additive group, not all the time additive group. Yes, it is the additive group of integers, but at times the additive group. We could equip it with multiplication and get to know exactly what happens. Now here, subgroups, when we talk about a subgroup, if you come across two groups, this one are two groups, G, S, of course you could do the same operation, binary operation. If this is plus, this one is plus. If this is multiplication, this should be multiplication. That if these two are groups under the same binary operation, and it happens that this S, of course these two are non-empty sets. If this non-empty set is a subset of these, then we say therefore that this one is a subgroup of this. So the binding thing is the same binary operation, and then this one is a subset of this. Then we call this S a subgroup, and that is exactly what we have here. We have S, of course, that is called a subgroup of G under the same binary operation. And some examples given here is the set of all integers under binary operation of addition is a subgroup of the set of rational numbers, and that is true under addition. What we have here is, look at this one compared with this, a set of rationals. Remember, this is not non-zero, so that is why we don't have note here, and then we could do with plus. You see, each one of these in its own right is a group, but now every integer is a number, so the set of integers is a subset of this. So meaning therefore this one is a subgroup of this. That is it. Okay. Yeah, that is it. These are properties of of subgroups, but I don't intend to take you through that. Those who have an inclination to pure mathematics can take that. So in my case, I don't intend to do that. Now, before talking about this cycle group, I'd wish to take you through this, and you're gonna notice that yes, this is a cycle group, and I wish to take you through this before the end of this lecture. And let me hope that you can see this clearly. And this is what we call the additive group of integers modular n. And we talked about last time what two integers that are congruent modular n. You see? And if you remember, we said that two integers x and y are congruent to y, that is mod m, if and only if m divides the difference. This one is the one that we're talking about, congruence. That x is congruent to 1 mod m if m divides the difference of these two. Now, when we talk about, look at this, I'm talking about one case of a set of integers, modulo 3. And this, we discussed equivalence classes last time. We say that this Z3 simply consists of equivalence classes of integers under an equivalence relation. And remember, last time we talked about, we say that concurrence modulo n is an equivalence relation. You see, we say that it is an equivalence relation. And here we're talking about concurrence modulo 3. And the set contains 0, 1, 2. And so you realize that Z3 is equal to, consider 0, 1, 2. You see, Zn, therefore, is 0, 1, all the way to n minus 1. You see, that is something that you should have in mind. But now you notice this one is an equivalence class. This one is an equivalence class. This one is an equivalence class. We talked about it last time. And we say it represents all integers that are divisible by 3. You can see 0, plus or negative 3. We could order this to be negative 3, 0, and then we order negative 6, or negative 9, negative 6, negative 3, 0, 3, 6, 9, and so on. 1 represents integers that leave a remainder of 1 when divided by 3. That is 1. You see, 1 divided by 3 is 0, remainder 1. 4 divided by 3 is 1, remainder 1. You see, negative 4 divided by 3 is negative 1, remainder 1. Is it? No, negative 2, remainder. What is negative 4 divided by 3? By the way, yes? Anyway, you need not bother yourself much. Positive 7 divided by 3. Let's go to the positives. Those ones are clear. But you notice that in the we shall have, if you have 7, then we have negative 7. Positive 7 divided by 3 is 2, remainder 1, and so on. 10 is 3, remainder 1. So here, 2 represents all integers. You see, these ones are the equivalence classes. That leave a remainder of 2 when divided by 3. When you go to 3, you realize that it takes you back to this. You see, because 3 is divisible by 3, and therefore it takes you back to this. So therefore, you notice that is why it takes you back to 0. So this is a set of equivalence classes. We call it the set of integers modulo 3. And in order that there is finite set of integers under the operation of addition and multiplication, where all calculations are performed modulo 3. So we could have even, look at this, we could have also multiplication. It doesn't have to be addition all the time. And you told the addition operation in Z3 is done by taking the sum of 2 elements, then reducing the result modulo 3. And we're going to see that. This structure is also called the additive group of integers modulo 3, if we're talking about addition, because it forms a group under addition. And you told that the set 0, 1, 2 and addition modulo 3 is closed. Yes. Whenever you add any 2, you'll always have a member of that group. That adding any 2 elements results in another element of the set. It will never go back to, it will never go beyond this. 1 plus 2 is 3, but 3 is 0, modulo 3. You see? Even 2 plus 2 plus 2 is 1, modulo 3. And that is when I think you've heard of that case where you're told that you've had mathematicians saying that 1 plus 3, there are certain times that 1 plus 3 is equal to 0. Yes, 1 plus 3 mod 4 is 0. It is not 4. 2 plus 3 mod 4 is 1. You see? So that is when now we say that, okay, mathematicians now have a different language. But now when they salute in the case of the congruence modulo, the equivalence relation is modulo n. You see? And you're told that in Z3 under addition, modulo 3, the additive inverse of an element is the element that when added to the original element gives the identity element, and the identity element in this case is 0. And to find, you told us find the additive inverse, look at that, of an element, you need to find an element, y, such that when you add them, it is equal to the additive identity. Like in this case, when we talk about 2 in Z3, what is the additive inverse? The additive inverse is, you see, it should be one that will give you 0 modulo 3. So the additive inverse of 2 is 1, because 2 plus 1 is 3. 3 mod 3 is 0. You see? Look at this. You're told that if y is equal to 0, then 2 plus 0 is equal to 2, which is not equal to 0, because ordinarily then it should give you a 0. Yeah? Should be congruent to 0. Now, when you look at y is equal to 1, then 2 plus 1 is equal to 3. And 3 is congruent to 0 mod 3. Why? Because when you say 3 minus 0, it divides 3. You see? So the additive inverse of that is it. And similarly, you can see this 0 as an inverse of 0, because when you add this, you will get 0, which is the additive identity. 1 plus 3, 1 has an inverse of 2. You see? 2 has an inverse of 1, and 1 has an inverse of 2, because when you add these ones are 3, and that is the same as 0 mod. That is the same as 0. You see? Mod 3. And I think up to there, we're going to meet next time, picking up from there. We shall talk about some few examples. And I think, let me see that. Yeah, we shall talk about what you call the Cayley, the cyclic group. After the cyclic group, of course, one of the cyclic groups is that is like a Zn equipped with that is, of course, Zn, the additive group of integers modulo m. That makes up a cyclic group, and we shall get to know exactly how that operates. And we shall come up with what we call the Cayley tables. Once we are done with the Cayley multiplication or addition tables, then we shall cross over to rings. We shall close that and then go to that is mathematical logic from where we left last time. So you guys have a good evening. Thank you for your attendance. This has been, let me see, how was the number? Or the number has gone down. It is 95, and I think it had come to around the number